Synthesis problems are going to be an important part of this course. Now, you learned a little bit about them in the previous class, and we had a couple of problems like those on the exams as well. So we want to continue to practice them, especially as we're learning more and more reactions. And just as a reminder, there's usually more than one way to solve a synthesis problem, especially as we start to learn more reactions. So if you ever have any questions about the way that you solved a synthesis, feel free to send me an email and ask me if yours is correct. So with synthesis problems, we always want to ask ourselves two questions. The first one, is there a change in the number of carbons? If the answer is yes, we want to figure out if we're reducing the number of carbons or gaining carbons. So based on the reactions we've learned thus far in this class, if you're reducing carbons, we know that we need a carbon-carbon breaking reaction. And the only one we know right now is ozonolysis. If you are gaining carbons, we want to think about our carbon-carbon forming reactions. And at this point, we've learned about the alkylate ion and Grignard reagents that allow us to form carbon-carbon bonds. We also want to consider whether or not there's a change in the type or location of a functional group. And if this is the case, we have to consider all of the other reactions we've learned so far in the class. So we'll start off with Chapter 13, number 51A. We're beginning with an alkene that has 1, 2, 3, 4 carbons. We are ending with a molecule that is an alcohol with 1, 2, 3, 4, 5 carbons. So we know that we have to add 1 carbon. And so far, we have 2 main reactions that allow us to add carbons to the molecule. We can either use the alkylate ion, which involves making and forming an alkyne, or we can use Grignard reagents. Which involve us using carbonyls or epoxides and creating alcohols. So since our final product contains an alcohol, we want to use the Grignard reagent method. Now our Grignard reagents can react with carbonyls or epoxides. Now in this case, there's a couple of different things we can do to use a Grignard reagent. First, we can turn an alkene into a carbonyl by using ozonolysis. So let's go ahead and do that. Now in ozonolysis, we're actually going to cleave a carbon, but it's still going to create a carbonyl. So we're going to be left with an aldehyde that has 3 carbons. So we've lost carbon number 1 in this case. But now we've set up this molecule to react with the Grignard reagent to create an alcohol at exactly the position that we need. Now we have 3 carbons here. We need to add a total of 2 carbons. So we can treat it with a Grignard reagent that has 2 carbons, such as ethyl magnesium bromide, and follow that up with water. So that's one way we can make this product. On the next slide, I'll go through a way of making the product using an epoxide. Now, epoxides can be formed from alkenes. So if we treat our alkene with MCPBA, we'll form our epoxide between carbons 1 and 2. Now we want to add 1 carbon to this molecule. Since we started out with 4, we only need to add 1 more. So we will treat it with methyl magnesium bromide, followed by water. Now we want to make sure that we're going to be attaching the methyl group to the correct position so that the alcohol ends up at the correct position. Now our Grignard reagent is a strong nucleophile. So that means it needs to attack the least hindered carbon of our epoxide, which is going to be carbon number 1. Now as the Grignard attacks carbon 1, we're going to add the methyl group there, and it's going to break the bond between carbon 1 and the oxygen of the epoxide. So now the oxygen is going to remain on carbon number 2. Then we will go ahead and protonate that oxygen. So if we look at what's actually happening in our final product, we will verify that our alcohol group is on carbon number 2. Okay, so 2 different methods to form the same product from the same reactant. In 51B, we're starting with the same 4-carbon containing alkene, and we're ending with a ketone that has 5 carbons. So we know that we need to add 1 carbon, and we also know that ketones come from alcohols via oxidation. Okay, so we can go through the same process as we saw in the previous step. We can go ahead and turn the alkene into an epoxide. We can treat it with a Grignard reagent to add 1 carbon, followed by water to protonate the alcohol. Then we can use an oxidizing agent to oxidize our secondary alcohol into a ketone. So we can either use PCC or we can use chromic acid, which are reagents we saw in chapter 12. So either one of these will accomplish the same reaction. In 51J, we're starting with an alkyne that contains 1, 2, 3, 4 carbons, and we're ending with an epoxide, and specifically a cis epoxide that has 1, 2, 3, 4 carbons. So there's no change in the number of carbons. We don't need to worry about Grignard reagents. We just need to worry about changing our functional group. Now our cis epoxide comes from a cis alkene. And we learned in previous chapters that we can turn an alkyne into a cis alkene using specific reagents. The most common reagent is hydrogen gas with Lindlar's catalyst or some sort of poison catalyst. So that's specific to turning an alkyne into a cis alkene. Then we can go ahead and treat our cis alkene with a peroxy acid, such as MCPBA, to produce our cis epoxide. Now in 51Q, we are starting with a molecule that has 1, 2, 3 carbons and a chlorine attached. So we have an alkyl halide and 3 carbons. We are ending with an aldehyde functional group with 1, 2, 3, 4, 5 carbons. So we need to add 2 carbons. And we also know that aldehydes come from either alkenes or the oxidation of primary alcohols. Now alkyl halides we can do a whole lot with, but specifically that might help us the most today is alkyl halides can be turned into Grignard reagents. So let's go ahead and do that and see what we can do. So to make a Grignard reagent, you react an alkyl halide with magnesium in a solution of diethyl ether. Now this is going to insert the magnesium between the carbon and the halogen. Now at this point, Grignards can react with either carbonyls or epoxides. Now we need to add 2 carbons in this case. Now if you react the Grignard with a carbonyl, such as a aldehyde, the alcohol group is going to end up at the wrong position. So let's go ahead and react our Grignard with an epoxide. And yes, you can use epoxides as reagents. Now we're also going to follow this up with water. Now, as the Grignard attacks, it'll attack our epoxide at either carbon, it doesn't matter which one, and kick the electrons up onto the oxygen. And that's going to extend our carbon chain by 2 carbons. Okay, so we've got 1, 2, 3, 4, 5. So carbon number 1 is going to form the bond with carbon number 4. And carbon 5 will end up with the oxygen on it. Now the water is going to protonate the oxygen on carbon 5 to make a primary alcohol. So then our last step will be treating this with PCC, which is responsible for turning a primary alcohol into an aldehyde. We cannot use chromic acid in this case because it's too strong of an oxidizing agent and will turn the aldehyde into a carboxylic acid instead. Okay, I'm going to go over one more way to solve problem 51Q. Now, in addition to aldehydes being formed from the oxidation of primary alcohols or from alkenes, aldehydes can also come from alkynes. And we also know that alkanide ions can form carbon-carbon bonds. Now, alkanide ions also react with alkyl halides. So let's go ahead and take this alkyl halide and react it with an alkanide ion. Now we only need 2 carbons, so we will have a simple alkanide ion. Again, those ions are negatively charged and are often stabilized by a positively charged sodium. Now in our alkanide ion mechanism, it's just an SN2 reaction, so the electrons in carbon 4 will attack carbon 3 and kick off chlorine as a leaving group. So that will immediately allow us to add 2 carbons to our chain. Now the reaction that we use to turn an alkyne into an aldehyde is hydroboration oxidation, which involves 9-BBN followed by hydrogen peroxide and sodium hydroxide. So this is hydroboration oxidation that we learned in the alkynes chapter. And that will allow us to turn our alkyne into an aldehyde, where the carbonyl ends up on carbon number 5. So for all of these synthesis problems, I invite you to try to solve them in multiple ways. That's the best way to learn the reactions in different ways. And again, if you have any questions about your answers, always feel free to contact me.